Okay, we're looking for an exact value. In this case, we have a trigonometric function on the outside composed with a trigonometric inverse function on the inside here. They're not the same, so we don't have sine and sine inverse or tangent and tangent inverse. There's not going to be any nice canceling out going on here. So whenever you have the inverse function on the inside, what I always like to do, and I would suggest you do the exact same thing, is we're going to make a let statement. We're going to go ahead and say let theta equal whatever the inner function is, that inverse function. All right, so what we're allowed to do next is, based on this let statement, we've just defined theta to equal whatever's on the inside. We can replace everything on the inside here with a theta. So we're trying to now find sine of theta. All right, replace the tangent inverse of 7/4 with theta based on what we just defined theta to be, which sounds a little confusing, but it's not that bad as you work a few of these. All right, next thing I'm going to do is go ahead and rewrite our equation we just created. I'm going to rewrite this instead of tangent inverse. I'd like to rewrite this in terms of tangent. So if we apply a tangent to both sides, we get tangent of theta on the left-hand side. On the right-hand side, as we apply a tangent on this side, you're going to get nice canceling out and just be left with 7/4. All right, so now we have tangent of theta equals 7/4. This is going to allow us to draw a nice right triangle from what we know about SohCahToa. Now, this isn't going to be to scale or anything like that, but I'm going to place theta down here in the bottom left. And I know from SohCahToa that when you have 7/4, this means opposite over adjacent for tangent. So labeling our side lengths, we have the opposite side is going to be 7. The adjacent side is going to be 4. And now our goal is find sine of theta. Well, from what I know about SohCahToa, sine is going to be opposite over hypotenuse. So we do know the opposite can be labeled as 7, but we don't know the hypotenuse yet. So let's do a little bit of work over here and find the hypotenuse. Maybe I'll call that C. So Pythagorean Theorem says a squared plus b squared equals c squared. So a little bit of algebra going on here. 4 squared is 16. 7 squared is 49. C squared's on the right-hand side. Let's make this into a power equation by adding together these constants. So we have 16 plus 49 gives us 65 equals c squared. To get c all by itself, to eliminate that square, we're going to apply a square root to both sides. So we get c as the square root of 65, and I don't think that's going to reduce down anything nicely. All right, so to finish this up, we want the hypotenuse. We just found that to be the square root of 65. So we can go ahead and fill that in. Now, this may not be the cleanest answer we can get to. We have a radical in the denominator, so maybe we choose to rationalize our denominator. How we do that is you take our fraction. We're going to multiply by the square root of 65 over the square root of 65. And what that's going to do is that's going to say multiply numerators. So we have 7 times the square root of 65. Then as we multiply our denominators, we have 2 copies of the square root of 65 multiplied together. So when you have 2 copies of the same thing, it's squared. That'll counteract the square root part. And we're going to be left with just 65 in our denominator without any square root over top of it. So this is probably the best answer we can get to here. There's not going to be any reducing down. I don't think that's going to be nice between 7 and 65. All right, so I hope this helps out as you're trying to compose together trigonometric functions and inverse trigonometric functions. Remember, whenever the inverse is on the inside here, do the let statement, draw the triangle, solve it down. You got this. They're not that bad. Keep practicing.